Hi, Joel. So,
Hi.
Yeah, so maybe we can start.
Yeah, fine with me.
Hi, Joel.
Yes, I'm fine.
You can start. Hi, Joel. Can you hear me?
Yes, I can hear you. Can you hear me?
Yeah. So you can start, Joel.
Okay. I should start right now. Should I start right now?
Yeah, you can start.
Okay, well, I'm really very pleased to participate, even if only from a long distance away in this meeting, especially honoring Deepak for many, many contributions he has made to statistical mechanics. I think I first met Deepak about 40 years ago. I know I invited him to give a seminar at Rutgers. I'm not sure exactly how that came about, how I knew about him. What I do remember is that he gave a beautiful seminar telling us some marvelous computation he was doing, exact calculations about numerating lattice animals. Anyway, I was very impressed, and Deepak has continued to do amazing computations. So I'm very pleased indeed to be here. The topic or title of my talk is Hidden Order, Hyperuniformity and Rigidity. I hadn't realized when I prepared the talk that I would be preceded by Duff. I assume it was Duff who was talking before, so you probably know more about hyperuniformity than I thought. But anyway, it will consist a combination of some old work and some new work, and the new work is a joint work with Subra Ghosh. So just to introduce the subject, say one measure of the degree of order in a translation invariant point process on d-dimensional space is the variance of the number of points in a region lambda, such as a sphere of radius r. Now, if you look at the variance as number of points divided by the volume of lambda, which is called absolute value, then in general, this goes to some constant value, or maybe actually it goes to infinity when you are at critical points. However, in some cases, in interesting cases, this variance divided by lambda goes to zero, and that's called hyperuniform, or before the word hyperuniform, we used to call it superhomogeneous. And as we shall see later, this corresponds to when the Fourier transform of the truncated full pair correlation, which I will explain later, goes to zero. Now, interestingly, when this Fourier transform of the point process, so I will always be talking about essentially the infinite system, and it could be as I said before, it could be a continuum space, an RD, or it could also be on a lattice. But when there is a gap, namely a region where S of k vanishes, S of k is always non-negative, but it can be zero. And if there is a set M in K space where this when S of k vanishes, then the system is transparent to waves with the wave vector k in this set. And it also has the property, and that's more of the new work I'll talk, something maximal rigidity. It means that the exact position of points in the region lambda is determined by the configuration of points outside lambda. So I will review some old results and describe some recent ones. So in general, consider translation invariant ergodic point process in RD in n lambda be the number of particles in a region lambda. You can always think of lambda as being some sphere or ball. And since the expectation value of n lambda is rho, a constant, I'm assuming that something is translation invariant times the volume of lambda. And I say for most systems, the fluctuations in lambda, which is just characterized by the variance, will grow as lambda. But some cases, which have some interest and which I'll talk about today, the variance of n lambda divided by the volume of lambda goes to zero. As I said, everything here applies. Lambda could be just a lattice instead of the continuum. Since n lambda is just the sum of the characteristic functions of where the points are, namely kappa lambda Ri is 1 if y is in lambda and 0. Otherwise, taking the variance, a simple computation will tell you that the variance of n lambda is the volume of lambda times the integral of g of r minus some other term. Now, g of r is a truncated full pair correlation function. Namely, it has a delta function just corresponding when you take the square, when you take n lambda, you'll get terms which are diagonal. So, and then it's usual truncated pair correlation functions. While this quantity alpha lambda of r is given by this integral, namely r plus r1 has to be in lambda, while 1 minus kappa lambda r1 means that r1 is not in lambda. Sorry. Yeah, when r1 is in lambda, then this quantity just vanishes. This is just a straightforward computations. And then from the previous slide, you see that if you make lambda grow like a ball, a sphere, then the limitless volume of lambda goes to infinity. The variance is just given by the integral of g of r dr, which is always non-negative. And hyperuniform systems are then the ones where this is equal to 0. So where g of r is 0, or if you take its Fourier transform, then you have at k equals 0 that this is equal to 0. And I'm not sure if, okay. So taking lambda to be a sphere is an averaging over what you get is that when for hyperuniform system, where the variance divided by the volume goes to 0, you get that the variance divided by the surface area of lambda is just given by this integral, where alpha d is defined in terms, again, of the average value of this alpha lambda. So it's given, I mean, use this as no, R is no scalar. So this is the first moment. R to the d minus 1 would be just a volume element over there. And so when this first moment is positive, it means that the variance of n lambda grows as the surface area of lambda. However, this integral can diverge, and when it does so, that means simply that the variance of n lambda divided by the area goes to infinity, which means that the variance of n lambda grows faster than the surface area, but the system being hyperuniform, it goes slower than the volume. And we'll see later for hyperuniform system, the growth of the variance, lambda depends on how fast S of k goes to 0 as k goes to 0. An obvious example, say, of such a hyperuniform system is a perfect crystal, which can may smear out by doing translations over a unit cell. And then a natural question is, can the variance grow slower than lambda, which would mean, can this integral go to 0? And it turns out that if you use lambda to be a sphere, that this cannot happen. It's not a trivial result at all. Of course, if you use lambda to be some rectangle and you have something on a lattice, perfect, then you could get something that the variance is even smaller than the surface area of lambda. But when you use averaging over a sphere, Joseph Beck showed that that's not possible. It's still an open question. What is the minimum value of this variance of the number of particles in, let's say, in a sphere divided by the surface area? Is it obtained for a regular lattice, or is it obtained for some other configuration? In fact, it's rather amusing. I think Joseph Beck and some collaborators proved a long time ago that there is a phase transition or a change at something like 800 dimension, where the minimum variance divided by the surface area changes from being on a lattice, just particles perfectly aligned on a lattice, or something particles uniformly distributed inside unit cells. Another question is, can equilibrium systems, standard equilibrium system described by grand canonical ensemble, be hyperuniform? Namely, but if you simply look at the number of particles in a fixed volume lambda, you use the grand canonical ensemble, you have a relationship between the variance and the derivatives of the density with respect to the fugacity. And then there's a theorem by Ginevra, again, that this cannot be, this cannot go to 0 as the volume of lambda goes to infinity. And which is an interesting result, and it tells you, I think, maybe related to what talking before I didn't get to see that, namely is that if you have an equilibrium system in the form of a crystal, like as we believe to be the case for three-dimensional hard spheres at high density, there must be enough vacancies and fluctuations that the variance grows like the volume, namely equilibrium systems in general at finite, not close packing density or not at zero temperature, cannot be hyperuniform. Of course, I mean, I think if I sort of surmise correctly, in the previous talk, they were about random close packing. Of course, that's not the equilibrium system, so that's a different story. And so for equilibrium system, you don't have it. It's more non-equilibrium system, at least when the potential decays sufficiently rapidly. Actually, the situation is more interesting when one considers system with long range Coulomb interactions. This is sort of was the most physically most relevant case. It's the case where one first obtained results for about hyperuniformity. And so this is just the usual Coulomb interaction, which is potential, pair potential. In one dimension, it just goes like the distance. In two dimension, it goes like a logarithm. In a higher dimension, it goes like r to 2 minus d. Means in three dimensions, 1 over r. And then much before sort of more current interest in hyperuniform system, it was shown that fluctuation in the charge in a given region lambda in a Coulomb system is hyperuniform. To simplify matters and relate the charge fluctuation to the number fluctuation, I will consider from only the simplest kind of Coulomb system, classical one-component plasma, which is also known as gallium, which was introduced by Wigner. It consists of particles with a positive charge, E, moving in a uniform background of negative charge with density minus rho E. Now, this incompressible translation invariant background, starting with a given origin, defining properly as you go, as the system becomes larger and larger, will produce a harmonic potential confining the particles, the positive charge particles. So in particular, in setting absolute values of charge equal to 1, you have, when you have n particles in such a uniform background, the potential is just a pair Coulomb interaction, which I mentioned before, which would be logarithmic in 2 dimensions, like 1 over the distance in 3 dimensions, plus a confining potential, which is a harmonic potential. Now, it can be shown that if you have now this canonical ensemble, and you take the limit as you increase the number of particles and you increase the domain, is that you will eventually have a limiting probability distribution, which, say, for finite n, it's just this canonical distribution with this potential reciprocal temperature beta. This measure has a limit, which is a uniform translation invariant density, where the density of the positive particles in this uniform background is given by rho. And this one component plasma, and the limit is exactly solvable in one dimension. In fact, Kuntz showed that it's periodic with period rho minus 1 for all non-zero temperatures. And the probability distribution of the number of particles minus the average number of particles in a region lambda, again, this is in one dimension, whereas the region lambda is just an interval of length L or length lambda, that this has an exponential decay, and the variance of n lambda in one dimension is bounded because it has independent of the size of the interval, it still has an exponential decay, and therefore it's certainly hyperuniform. In fact, it is proportional to the surface. In one dimension, the surface is just a constant, just a number 2. So actually, quite generally, it's true that if you have a system in one dimension which has a bounded variance, the variance does not grow with the length of the interval you're looking at, then you have to have a periodic component. In this case, it's perfectly periodic for the Coulomb system. In 2 dimensions, the one component plasma is translation invariant at small beta, meaning at high temperature, but for large beta, meaning at low temperature, the system is expected to form a periodic Wigner crystal. And as I say, in this case, system will be hyperuniform. And in 2-dimensional fact, the system is exactly solvable at beta equals 2 using the units. Remember that E is equal to 1. And at this temperature, the particles have the same distribution as the eigenvalues of a complex Gaussian matrix, a non-Hermitian. This is so-called Ginebra ensemble. When you take a random matrix, each of its elements is a Gaussian. It doesn't have, so the eigenvalues will be complex. It's not Hermitian. Then if you do the right scaling on those eigenvalues, you get a probability distribution of points in the complex or on the plane, which is exactly the same as you have for the one component plasma at beta equals 2. And at that temperature, you can actually compute the pair correlation function exactly, and it's a Gaussian, very, very good clustering properties. And you can just see that the integral of G of R dr, this is now the volume dr, is exactly 0. So as expected, in general, for the charge systems, you have hyperuniformity for this system. So I would like to mention some other examples. I don't know if it was already done before, but anyway, some systems which are hyperuniform. I'll begin with some natural system which appears to exhibit hyperuniformity. I will then consider determinantal processes, which are of much current interest in a large class of which exhibit hyperuniformity, and then go on to some other systems. So this is a very interesting example taken. This is taken from a figure in the magazine Wired. It shows the cones, the visual cones in the eye of a chicken. And you have 4 different cones over there indicated by different colors. Now, this doesn't look hyperuniform at all, but when you look at it, I mean, if in fact it is, in fact, when you look separately at the colors, you can see that there's a kind of order. In general, for hyperuniform systems, you will have some kind of a repulsion between the particles, which makes them go. So this is quite, I find it quite interesting and included here. By considering the cone type separately, we can see that each cone is surrounded by an exclusion region. Anyway, that sort of, it makes it look much more uniform than when you look at all of them mixed together. So determinantal processes, I'm not sure how many, how much this is known in the general physics community, but it's a very interesting class of processes, namely there's a case correlation function. So again, we have the process in d-dimensional space, and you can also do it on the lattice, but I'll do it d-dimensional space, and you look at the k correlation function, and this is given by a determinant with some kernel k, a capital K. So namely, if you want to look at the little k correlation function, you have to take this determinant. And given a capital K, I'll take here to be Hermitian, whose eigenvalues are in 0, between 0 and 1, this is proven to determine a point process. In a point process, when k equals 1, that just gives you the density. When k equals 2, doing this, you get this determinant. So rho 2 is given by just pair correlation, is given by rho squared minus this determinant, minus this kernel k squared. That just comes out from writing out this determinant. So here in general, determinantal point process, general is true that the determinantal point processes whose kernels are projection operators are hyperuniform. Can be seen, by doing the computation or the general theorem on this effect. When you integrate the truncated full pair correlation function, you'll get that the integral is equal to 0. In this, the projections being the kernel being projection operators means simply that the eigenvalues are either 0 or 1. And as this happens in many cases, in particular, the Genebra ensemble, which I said was the same as a 2-dimensional one-component plasma at B equals 2, it's a determinantal point process with a projection operator, so it's hyperuniform. In one dimension, you have so-called Dyson lagas, namely particles are confined to a line, but their interactions are logarithmic, and then the variance grows like the log of the length of the interval, lambda, and a length interval, and on the line it grows like the log, which is faster than the surface area, but smaller than the volume. And the same turns out to be the case for an ideal Fermi gas of n particles in a region lambda in any dimension, which has a wave function given by a Slater determinant. And again, one can show that this is hyperuniform. Here is this, I don't know, again, if this was discussed, but a system that I and some colleagues have been working on, which Duff Levine and his collaborators have studied, namely, you are on a lattice and particle can jump to a neighboring site if it's empty, but it can only do this jumping if it also has an occupied neighbor. So it's facilitated exclusion process. Namely, the simple exclusion process is just where particles can jump to a neighboring site if it's empty. But as a facilitated exclusion process, it can only do the jumping if it's if it has one occupied neighbor also. So starting with a Bernoulli product measure, just the independent density rho, the system approaches ST infinity, either a frozen state in which all particles are isolated, or an active stationary state in which there's a finite density of active particles. And transition in D equals 1 is exactly a density 1/2, at which density stationary state is periodic. Now, the remarkable thing is that D equals 2, it was found, I guess Hexner and Levine found also that there is a critical density when the system, starting with a product measure, changes from going to a frozen state where all the particles are isolated, going to an active state where a finite fraction of the particles are active, is hyperuniform. I think this is really remarkable. And unfortunately, absolutely no rigorous result on the system beyond one dimension. I won't go in any more with this. Okay, so let me go. No, I think from the beginning, now some the new results, which are joint work with Subra. So we consider the case, I guess, which Torquato called, you have a stealthy hyperuniform. Namely, that if you look at the structure function, the Fourier transform of this truncated full pair correlation function, is 0 in a given set M in K-space. I mean, K-space itself, if you have a system's a continuum RD, will also be D-dimensional, while if you are on a lattice, then it will be just a torus. Anyway, so this is a special class of hyperuniform systems if K equals 0 is included in this interval, M, where the structure function vanishes. As already mentioned, S of k cannot be negative from its very definition, so it can be positive or zero, and so if it's zero in a given interval. And this is the reason for calling it hyperuniform, calling it stealthy, because it is transparent to acoustic waves which have their wave vector in this interval. So what we did, some work with Subro on this stealthy hyperuniform systems, that they have zero probability of having holes larger than a certain diameter, namely in d dimensions. You have that there is actually zero probability of having an empty region which is bigger than a certain value of d naught, which depends, d naught itself, how big it is, depends on how large the gap where the structure function vanishes. This was conjectured by Zhang and by Torquato et al. And we were able to prove this rigorously. In fact, we also proved upper and lower bounds of the density of particles in any region. It shows the fact that most configurations will be what's called in some literature Delaunay sets, namely that you never have more than one particle in a ball or sphere of size d naught or smaller, and no holes larger than d naught. We were able to prove this rigorously for such a case. In the same work with Subra, we generalized the notion of stealthy process to consider a situation where S of k vanishes in an open set M, which we need not include the origin k equals 0. We call these generalized stealthy processes. In what we show, that's a sort of the very interesting part to me, at least, that a generalized stealthy processes, such system, have a remarkable rigidity properties. So to describe these rigidity properties, let me go back to the general point process in RD or D. So I have been discussing so far the variance of the number of particles in a region lambda when you have a translation invariant infinite system on the d-dimensional space or a d-dimensional lattice. But let's consider now the case, what happens when you look at a region lambda, but you specify the configuration in the complement of the region lambda. What can we say about the distribution of points inside the region lambda, given the configuration in the complement of lambda? Namely, we want to know the conditional probability, probability density of having a configuration X, X is a whole configuration of lambda, given the configuration in the complement of lambda outside. Now, for the case of Gibbs measure, this is a well-known DLR equations, namely, if you want to know what's the probability density of having particles at positions x1 to xn, given the configuration as a complement, it's just the Gibbs measure given the potential energy for the configuration of particles in lambda once you specify the configuration in lambda complement. So in general, when the interactions you decay sufficiently rapidly with distance, and the measure is ergodic. It's not a superposition of two extremal measure the behavior of the variance in some region lambda prime inside lambda. When lambda becomes very large, it's just as we had before when we didn't consider the boundary condition. Again, this is not the case when you have long-range Coulomb interactions, where in fact the potential energy of the particles inside lambda, given the configuration outside, is not well defined because the potential is such a long range. Now, Eisenman and Martin proof for the one-dimensional Coulomb systems, including the one-component plasma, I mentioned that the charge in an interval AB, which is lambda, just an interval, which corresponds to one component plasma to the number of particles in lambda, is uniquely specified by the configuration in the complement outside of this interval. Quite remarkable thing. This is true for all typical configuration, namely all atypical configuration has measure 0 with respect to this probability measure on this infinite system. This property, that's a probability of the number of particles in lambda given the configuration in lambda complement, is concentrated on a single value of n lambda, namely, given the configuration outside, you know exactly how many particles there are. It's called number rigidity by Gaussian pairs. But Gaussian pairs showed, for example, the Geneva ensemble and the standard plane Gaussian zero process, namely, you have an infinite sum with the AN being Gaussian random variables. If you look at the zeros, that these have got number rigidity, namely knowing the configuration outside tells you exactly what is the number of particles inside. Both the Geneva and the Gaussian unitary ensemble sort of correspond to Coulomb system. And Gaussian pairs showed that these systems, that while the number of lambda is fixed by the configuration and the complement, the distribution of points inside lambda is not rigid. In fact, it is absolutely continuous with respect to Lebesgue measure. And the same is true for the one-dimensional Coulomb system considered by Eisenman and Martin. In work with Subro, we show that the number rigidity, in fact, holds for all hyperuniform systems in 1 and 2 dimension, satisfying a certain decay assumption on the pair, on the truncated pair correlation function. And however, or prove that hyperuniform systems with a sufficiently rapid decay of correlation, of the pair correlation, has got this number rigidity, does not work in 3 dimensions. In fact, there is strong evidence from some work of Paris and Saclay that no condition on the decay of correlation would work dimension C. This is such an interesting result, which I'm interested. Let me just briefly show. It says Paris and Saclay show that the independent, identically distributed perturbed lattice point processes, namely, you start with points, particles on every lattice side. And now you perturb it, namely, you move independently each particle a distance x away. So if y is the lattice side, you move it to y plus x with probability h of x dx. Clearly, if h of x has got a first moment, then it's easy to see that this system will be hyperuniform. But what Paris and Sly showed, that it's also rigid in one dimension if the perturbation have finite first moment, which is consistent with the criteria mentioned before, which Subra and I proved, and also rigid in 2 dimensions. However, there is a remarkable phase transition in its rigidity behavior for Gaussian perturbations, namely where probability of displacing the particle from its lattice side is given by a Gaussian in 3 dimensions. So there is a critical value of the covariance sigma, such that if the covariance is smaller than a certain amount, then it will be also rigid, namely the number of particles in a given region will be determined exactly by outside, but it's not rigid if you go beyond that. So going beyond number rigidity, Kash and Krishnapur define a hierarchy of rigidities by checking the number of moments of the distribution of particles inside lambda, which are determined by the configuration in the complement of lambda. So number rigidity only requires that the zeroth moment be determined. Maximal rigidity corresponds to the actual configuration in lambda be determined with probability 1 by the configuration outside lambda. This means that the distribution of points in lambda given the configuration outside lambda is essentially a delta function. And this is the case, of course, if you have perfect crystal. But now comes the punchline. We prove that all generalized stealthy processes, namely processes where you have an open set in the Fourier space, where the structure function is 0, are maximally rigid. And question is, can you construct such processes? And the answer is yes. This can be constructed even for processes which have normal fluctuation, can be. One can construct generalized stealthy processes for Gaussian processes on a lattice. So this maximal rigidity is true not only when you have particles on a lattice, but when you have some general functions on a lattice. I think I won't do that since I'm running over time. So let me just say that you can find all the references in these 4 papers with Subra Ghosh, and thank you very much for your attention. Are there any questions or comments?
Yeah, thanks, Joel. So any questions?
Should I stop sharing my screen?
Okay.
It says stop share, but nothing happens.
Sorry,
I don't know how to stop sharing.
Joel, I want to thank you very much for your kind words and the fact that you joined us for this meeting. Can you hear me?
Yes, I can hear you.
So I was just saying that I thank you very much for your kind words and joining this meeting. The structure of the hyperuniform sets is very interesting. Do you have any comments about this idea that all these RCP random closed peg structures show hyperuniformity? Is that a definition, or is that
I do not know. I haven't really thought about that, so I cannot answer that question. At least I haven't thought about it in a way that I can answer the question. But it's certainly interesting to look at such systems.
Oh, can you hear me?
Yes.
So at some point you said that hyperuniformity cannot exist if the surface is a sphere. surface of a sphere.
Cannot exist what?
On a surface of a sphere. If the region is a sphere, yeah.
I'm sorry, I do not hear. It cannot exist for equilibrium systems with sort of decaying potential.
No, it cannot exist on a sphere. If the region is a sphere.
No, I didn't say that. I don't think. You can have hyperuniformity, but the variance must grow at least like the surface area. It can grow faster than the surface area, but smaller than the volume, but it cannot grow slower than the surface area when you do spherical averaging. That's correct.
Okay.
That's what Joseph Beck proved.
Okay.
So, but certainly your whole space could be a sphere. I haven't thought about the non-Euclidean spaces. You have some similar results, certainly.
Okay, so Joel, I had a couple of questions. So one is, I mean, so in for one-dimensional systems, for the Coulomb gas, you said it's hyperuniform. But what about like other long-range power law interactions? So is it that any long-range interactions leads to hyperuniformity?
I don't know the answer to that. I mean, I think if the interactions go faster, certainly probably than 1 over r squared, then and if you have equilibrium systems, then they will not.
But if it's slower than 1 by r square, let's say. If it's slower than 1 over r square in one dimension, in that case, is it always hyperuniform?
I do not know the answer to that. If you, it's a good question, but I don't know the answer. I mean, I don't know. I can't. But as I say, system studied is the Coulomb system, where the interaction itself is linear in the distance, and you have a very strong hyperuniformity effect in one dimension. I think, as I mentioned, the one component plasma, classical one, is periodic. And I think the results, quantum mechanically, again, I think you get periodicity at least below a certain temperature in one-dimensional Coulomb system. So that's I mean, very strongly hyperuniform. Because
so supposing we take the in one dimension like a logarithmic interaction, in which case the density is of course not uniform. We get the Wigner semicircle. I mean, in that case, can one talk about hyperuniformity a bit?
Are you asking in one dimension with logarithmic?
Yeah, in one dimension with a logarithmic interaction, where you get the Wigner semicircle.
The answer is yes, that's hyperuniform, but the variance grows slower than the volume. Let's say the volume is the length of the interval L. It goes slower than that, but faster than the surface. The surface in one dimension, just being like a number 2, it grows like the logarithm of the length of the interval. So yes, it's hyperuniform because the variance grows slower than the length, but much faster than the surface area. It grows like the logarithm. And in fact, a long time ago, some joint work with Ovidio Kosten, we proved that if you take the number of particles, truncate an interval divided by the square root of the log of the length of the interval, it approaches a Gaussian, it satisfies a central limit theorem.
Yes, one can say that the
I'm sorry?
uniform, but it is hyperuniform.
It is hyperuniform. Yeah, because if you divide the variance by the length of the interval, it goes to 0.
I understand, but I'm saying that, but the density itself is not uniform. That is what, so it, why should we call it hyperuniform?
The density is uniform. Why do you say it's not uniform?
Not for the log gas.
Hmm?
Not for the log gas in 1D. That is the Wigner
Yes, the
circle.
density, why isn't the density uniform? I mean, the density is
No,
uniform. Maybe we are talking about different systems, but if you take the system, this Dyson log gas with logarithmic interaction, if you take the infinite volume limit on the sphere, you get something which is uniform. I mean, what kind of not? I mean, it could be periodic or something like that. Is that what you're talking about?
Yeah, so I was saying that if you take the distribution which is the eigenvalue distribution for which Wigner circle law holds.
Well, you have to scale things properly. So you have to scale things with the right factor so that you get a uniform density. The same is true in 2 dimensions. You have to, yeah, sorry, I should have said more clearly to get the eigenvalue distribution to correspond to the one component plasma particle distribution, you have to scale it. You have to scale it with the right way so that you have a density rho. But that's straightforward. You just scale, I mean, you have in general, yes, of course, it's not uniform, but if you do scaling and you let the size of the matrix or system go to infinity, then it goes to a uniform distribution, which is hyperuniform.
You said the ideal Fermi gas is an example of hyperuniformity, if I understood correctly.
At zero temperature.
And immediately at non-zero temperature, it becomes regular. Is that correct?
I think that's correct, yes.
So that sounds a lot like the distinction between entanglement entropy of ground states and of non-zero temperature states.
Could be, I don't know.
The connection?
I probably, but I don't know exactly. I would think, so I'm not sure anybody has proven it, that the Genebra theorem about equilibrium systems at finite temperature not being able to be hyperuniform, maybe having a variance which grows like the volume always for quantum systems, but I would expect that that would be the case. So indeed, as soon as the temperature is not zero, you would get variance proportional to the volume. That's what I would certainly expect. But I don't know of any proof of that.
So just one more question. You know, you discussed one component plasma.
Yes.
Have 2 component plasma with plus and minus charges. Can one say that the charge still has a hyperuniformity in some cases?
Absolutely, always. That's exactly what happens. In fact, very interestingly, imagine as you in real life that, let's say, if you're at intermediate temperatures or what, is that the charges form atoms or molecules. So you should imagine, you could imagine like you have a match, a little stick on one side, one end of which is plus, other one is minus. But the system is overall neutral. Now, if you look at given volume and you ask for the charge fluctuations in that volume, the only place where you would get possibility of not being perfectly neutral is at the surface where this little stick is cut by the surface, having the plus or minus inside and the other end outside. So in fact, so you get a variance of the charge distribution, which is proportional to the surface. That's really the more physical situation. I just use a one component plasma to make it look exactly like number fluctuations and to make it simpler. But yes, the basic theorem are indeed that the charge fluctuations are hyperuniform.
Coulomb log gas, also this will be true?
I'm sorry?
Two-component Coulomb gas, would this be true at high temperatures?
I'm sorry?
2D Coulomb gas at high temperatures. Log
Yes,
gas.
yes, exactly. The charge fluctuations will be hyperuniform, I expect, growing like the surface area.
Is that somehow in tension with the usual textbook descriptions of the Kostelis-Thouless transition as a transition between dipoles of vortices and high temperature phase where the vortices are unbound? That's just a heuristic picture.
Be, I don't know, but I don't think it's the same. I think the hyperuniformity for the charge fluctuations will hold in all cases, whether you have sort of bound states or not. I'm not sure exactly. I think the proofs going back to Martin Yeltsin and others from the 60s, also Van Beren or what, make rather weak assumptions about the Coulomb systems to conclude that you have to have hyperuniformity. It's a long range of the Coulomb interactions are such that there will be, it's essentially a Debye screening type of argument. That's if you have a positive charge somewhere, it will be surrounded by negative charges and vice versa in such a way that it's screened. And once you have such screening, then this leads to the hyperuniformity of the charge fluctuations. So it's a more fundamental property really related to the strength of the Coulomb interaction in its very long range.
Okay. I had one last question. So for this GS case, where this generalized stealth process, where you don't have the structure function, it doesn't vanish at k equal to 0. So in that case, it's you lose hyperuniformity. Is that right? It's still rigid, but you lose hyperuniformity. Is that right?
Yes, if the gap does not include the origin, then you lose hyperuniformity, but you still have this rigidity, maximal rigidity, which is, I find, very remarkable. I'm sorry, just not enough time to go through sort of the basic arguments, the way one shows these things. Yes, but it's true. So if you look at the references, you'll find the proof of this fact, but that's correct. You don't need, you have these generalized stealthy processes, and you could have variance growing like the volume, but nevertheless have this rigidity.
Okay. Are there any questions from people who are online? Chris, Sanjib? No.
No questions, thanks.
No questions.
Okay. Okay, so I think, Joel, then no other questions. Thanks a lot for joining
Thank
us.
you. Thank you for this invitation. And congratulations, Deepak, and all good wishes.
Thank you
Thank
very
you
much.
very much.
Bye-bye.
Thank you. Bye-bye, everybody.
Bye bye.
I